Hello, this is pre-lab lecture, lab 7, acids, bases, pH, and buffers. So in the lab, you guys are going to be talking about or doing calculations on pH. You're going to be measuring the pH of certain substances as well. So we'll go through some of those topics today. So an acid is a proton donor, or donates an H plus, an hydrogen ion. Example that I like to use is this HCl, which if you put it into water, it's going to dissociate to give us this H3O plus and Cl minus. You'll also see in some text, and we'll talk a little bit later, but H3O plus is the same thing. This is the same reaction as HCl, aqueous, dissolves to give us H plus and Cl minus. So these two are identical. It dissociates about 99.99%, but so it dissociates almost completely, but still there is a little bit of back equilibrium. Therefore, I wrote the reversible reaction as well. But we won't focus on that too much in this case. So an acid is a proton donor, and a base is a proton acceptor. It accepts the H plus. So in this case, if you look at this reaction, you have HCl, hydrochloric acid. It's an acid. It will give up its H plus to the base, in this case, which is water. So the H plus will move over to the water, and you'll form the H3O plus and Cl minus. So here's a different example where the H2O, water, acts as an acid this time. And why is that? Because we have a base here, NH3, and remember the bases will accept the hydrogen from the acid. So the hydrogen will move over here to the NH3 and become NH4 plus. And once you lost the hydrogen here from the water, what's left is OH minus. And this is a basic solution. So in this case, the NH3 acts as a base, the water acts as an acid. In the previous example with HCl and water, the H2O acts as a base. So we call water amphoteric, which means just like an amphibian, like a frog, the frog lives on land and water. Water acts as amphoteric, means it can act as an acid or a base. This new concept, maybe you've seen it in the lecture, conjugate acid-base pair. That means that when you have a substance in an acid-base reaction, again, we have an acid-base reaction, acid reacting with a base, in this case, the water acts as a base, they differ by one hydrogen. So a pair means two, so in this case we have HCl, and it will pair up with one of the products. And how do we know which one it pairs with? It differs by one hydrogen. So in this case, if we look at the products and compare it with HCl, the Cl minus is a conjugate base of the HCl because the difference between these two is one hydrogen. We said that the water acts as a base and its conjugate acid pair is H3O plus. The difference between these two is that it differs by one hydrogen. So chloride is formed, we read here, chloride is formed from the HCl, and H3O plus is formed from the water. So I want you guys to try an exercise. In this case, identify the conjugate acid-base pair. First, we see here that ammonia is a base, and HF, hydrofluoric acid, has to be the acid if the NH3 is a base. So what's going to happen here is the acid, the H from the acid will give up and go to the NH3, and the product is NH4 plus, and you're left with F minus. Remember, H has a plus charge. So what are the pairs? Again, the conjugate acid-base pairs, they differ by one hydrogen. So looking at the NH3, which product differs by one hydrogen? Yes, it's the ammonium ion. So this is the acid-base pair, and they differ by one hydrogen, with the NH3 being the base, and its conjugate acid pair is the NH4+. So by elimination, the HF and the F- are conjugate acid-base pairs. They differ by, again, one hydrogen. So let's write the conjugate base of the following examples. You can pause the video now and try on your own, but the conjugate base, H2S is an acid. How do you differ by one hydrogen? Well, the product you'll get is HS minus plus H plus. So again, this would be the conjugate base of the H2S. They differ by one hydrogen. And how do we know that it's a HS minus? Well, if you recall, H plus on its own, if you remember the charge state of S, it's 2 minus. So the overall charge has to be -1. The next example, HI, hydroiodic acid. So HI, its conjugate base would be I minus. Why is that? Because when the HI reacts with water, the H is lost. It gives up its hydrogen to the water, and you're left with I minus, and the other product, if it reacted with water, would be H3O plus. Carbonic acid, the third case, this is an acid again. It gives up its hydrogen, and therefore its conjugate base would be HCO3 minus. Recall that H will be plus, H plus, and CO3, do you know remember the charge of CO3? It's going to be 2 minus, so plus and 2 minus gives us an overall charge of -1. Next set of questions, what is the conjugate acid of the following pair? So again, these are all bases. If it accepts a hydrogen, it's going to be NH4 plus, NH4 plus. For OH minus, if it accepts a hydrogen, it becomes water, so its conjugate acid is water. And for the sulfate ion, 2 minus, if it accepts a hydrogen, it becomes HSO4, yes, minus. Strong acids. Perhaps you talked about this in lecture. There are 7 strong acids. If you remember, I just said strong acids, they give up their hydrogen, they give up their proton, they dissociate or ionize 100%, or you can say 99.99%. So in this case, we have the HCl gas. If it's a gas, it's hydrogen chloride plus H2O, giving us H3O plus and HCl. Sorry, and Cl minus. This is an example of a strong acid. There are 7 strong acids that you need to be familiar with: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. If it's not one of these 7 strong acids, therefore it's going to be considered a weak acid. Again, an acid is something that gives off a hydrogen. And usually it's found in the front part of the formula, in the front. These are all located in the front. There are some exceptions, of course, but in general, they're usually found in the front. So as I just said, if it's not one of the 7 strong acids, it's a weak acid. So here we have carbonic acid. So H2CO3, it's a weak acid. We also know it's a weak acid because of this equilibrium symbol, which means it does not dissociate 100%. It goes back and forth. So it's not as powerful of an acid. You're not going to get a lot of H3O plus compared to a strong acid. You're going to get a lot of back and forth. So you get a lot of H2CO3, you get a lot of H3O plus, and you get a lot of HCO3 minus if you had a beaker of this. Another example which you'll be doing in the lab, using in the lab as well, is vinegar, CH3COOH, acetic acid. Some textbooks you write the H in the front, but in our case I would like to write it CH3COOH, and this serves as an acid, and its conjugate base, just to review from the previous slides, its conjugate base is the acetate ion. Acetic acid is the acid. This water here is a base. In the product side, this acetate ion is a base, and the hydronium ion is an acid. So the conjugate acid of the water is H3O plus. So the question, what is the conjugate acid of water? For example, 1 and 2, I think I've said this already. The conjugate acid, this is a base, the conjugate acid would be the H3O plus. And in this example, again, it would be H3O plus again. So what is the conjugate acid of water in both examples? The answer should be H3O plus. So here there's an error in the key. You should say H3O plus. So we've talked about strong acids and weak acids. Now we'll look at talk about strong bases. So strong bases, when you put them in water, they form this OH minus, the hydroxide ion. And the strong bases form with group 1A, if you remember, alkali metals and alkaline earth metals, group 1A and 2A in the periodic table. So these are all examples of strong bases. They will form OH minus in water, hydroxide ions, and they are in the group 1, the metals in the group 1 or group 2. These are all group 1s, and this one, the calcium, barium, and strontium, are in group 2. So these are all strong bases. And as you can see, if you dissociate them in water, you will get Ca2 plus and OH minus. You have to put a 2 here to again balance our chemical reaction. If they do not, if they are not part of group 1A or 2A and they don't produce OH minus, you can consider them weak bases. So here are some examples. Weak base is the acetate ion. Remember, bases want the hydrogen. So in this reaction, it's going to grab, the negative charge is going to grab the hydrogen to form acetic acid, again a weak acid, and you're left with OH minus here. The ammonia, which I talked about in the beginning slides, grabs a hydrogen. In this case, the water acts as an acid, and you form with NH4 plus and OH minus. So identify each of the following as a strong acid or a weak acid or base. So in the first case, HBr, it's one of our 7 strong acids, so it's going to be a strong acid. Question B, here's an acid, it has an H in front, but it's not one of the 7. HNO3 is a strong acid, but HNO2 nitrous acid is not, so this is a weak acid. C, NaOH, is a strong base. Na is in the group 1. OH minus is produced, so this is a strong base. D, sulfuric acid, is one of the 7, so strong acid. And this copper 2 hydroxide is a weak base. Copper, as you know, is a transition metal. So recall our weak acid here as an example. CH3COOH plus water gives us CH3COO minus plus hydronium ion, we can write a general expression for this, a mathematical expression where we take, this is a HA, so that's just a generic acid. If we write the products, the concentration of the products here, divided by the acid, HA, you can develop a acid dissociation constant, which will tell us how much of the acid will dissociate. So we'll go through some examples in a second, and we do not write, a little bit beyond the scope of the class, we don't write the water in the denominator because the concentration of water is so high compared to the other species, we actually give it a value of 1. So if you see the water as a liquid, we do not write it in our equilibrium expression, nor do we write solids, and we'll talk about this later. So I just said earlier, why write a equilibrium, a acid dissociation constant? Because it can tell us how powerful our acid is, which means how well will the compound dissociate to produce our H3O plus or H plus. So if we look at this table, the larger, the higher the Ka value, the more powerful the acid. I don't want to use the word strong acid, weak acid, because we've already said there are 7 strong acids, so I'm just going to say the more powerful the weak acid, and the less powerful the weak acid in this case. So hydrogen phosphate is a not very powerful acid versus phosphoric acid, which is not one of the 7 strong acids, but it is a powerful weak acid. So again, we write the equilibrium expression. This is the products. So we wrote the products on top, divided by the CH3COOH, the acid that goes on the bottom. And we write here the equilibrium constant, 1.8 times 10 to the minus 5. And this value you do not have to memorize. This comes from tables. So here we have, the question is write the acid dissociation constant expression for the following. So it's HPO4 minus. So if they say this is the acid, so here we write, well, first we have to write a reaction. So here we have, if we put it in water, what's going to happen is this will be taken by the water. So the H2O will act as the water, and you're going to get H3O plus. And what's left is HPO4 2 minus. So if I want to write an equilibrium expression, again, it's products, so this is the top, products divided by reactants. So here it's done for you. The Ka expression is H3O plus, the products on top, HPO4 2 minus divided by H2PO4 minus. And we'll talk a little bit about this more in the buffer section. Another example here is an acid. When you react this with water, you get, so let's put the water here. This H will move over here. You'll get H3O plus, and another product will get, you're left with HS minus. So again, when you write the expression, again, it's products on top divided by reactants on the bottom. And again, we don't write water because it's a liquid. It has so much, the concentration is so high compared to the other species that we give it a value of 1. Next topic is ionization of water. So as you guys know, water is a unique solvent. It can act as an acid or base. It's amphoteric. So if we had a beaker of water, so if we had some water molecules in a beaker of water, you would get some H3O plus and OH minus. However, they would be in equal amounts, so they would cancel each other out in terms of their charge. You can simplify this reaction and write H2O gives us H plus and OH minus. So this is, we call this a KW, the expression here, the ionization of water. We write again products over reactants. So products over reactants. Again, we do not need to include the H2O because it's a liquid. So the expression, the equilibrium expression for KW, we call it KW as opposed to Ka. Ka, the A is for acid. KW for water. It's simply H plus times OH minus, the product constant of water. So I'm just going to rewrite what I just wrote, and this should happen at 25 degrees Celsius. Don't worry about the temperature at the moment. So if experimentally, if we had pure water, the hydrogen concentration would be 1 times 10 to the minus 7. And because water has a pH of 7, it's neutral, the amount of acid should equal to the amount of OH minus, the base. So if the H plus is 1 times 10 to the minus 7, the OH minus also has to be 1 times 10 to the minus 7. And if we multiply the two in the expression for water, we get 1 times 10 to the minus 14 when we multiply those two. So this is the equilibrium constant for water. Kw is 1 times 10 to the minus 14, and I'll circle this, and I'll circle it again because you're going to use this value in your calculations for the lab as well. So we have three situations for acidity. We have a neutral solution when the H3O plus equals to the OH minus. We have an acidic solution when there's more acid than base. And we have a basic solution when there's more OH minus than H3O plus. Another way to express this graphically, when it's neutral, pH is 7, the amount of H3O plus and OH minus stays the same. Again, H3O plus, you can replace that with H plus. And when we're in an acidic solution, we have more H3O plus than we do OH minus. And in the basic solution, we would have more OH minus than H3O plus. Again, our equilibrium expression for Kw, 1 times 10 to the minus 14. So a typical question is, what is the H plus concentration of a solution if OH minus is 3 times 10 to the minus 9? So we use this expression up here, Kw. We know Kw, 1 times 10 to the minus 14. In the question, it tells us the OH minus is 3 times 10 to the 9 to the 10 to the minus 9. So if we know these two values, hopefully you'll be able to figure out the H plus concentration, the third variable. And use that by 1 times 10 to the minus 14 divided by 3 times 10 to the minus 9 gives us 3.3 times 10 to the minus 6. Let's try an example. If orange juice has a H3O plus concentration of 3 times 10 to the minus 4, what is the OH minus concentration? So I'll set it up for you. Again, it's 1 times 10 to the minus 14, which is our Kw, and we're going to divide that by H3O plus, which is 3 times 10 to the minus 4. This is where you will have to use your calculator and be careful. Sometimes you might have to put a bracket in your calculator between here so then you don't make an error calculation or get, for instance, some of you might get 3.33 times 10 to the minus 18 That's not right. It should be 3.33 times 10 to the minus 11. So please make sure you get this on your calculators. And the M stands for molarity, the unit for concentration. So hopefully you're familiar with this. If you have a neutral solution, the pH scale, which is a measure of acidity, is 7. If it's less than 7, the pH is less than 7, we have an acidic solution. And if the pH is more than 7, we have a basic solution. In the lab, you would have used a pH meter, which is a nice instrument to give you the pH value. You simply dip the electrode, there's electrodes here, into the solution, and the machine will give you a readout. If you have an acidic solution, the H3O plus concentration will be greater than 1 times 10 to the minus 7. If you have a basic solution, the H3O plus will be less than 1 times 10 to the minus 7. And if you have a neutral solution, which means you have an equal amount of H3O plus and OH minus, you'll get the H3O plus to be 1 times 10 to the minus 7. So here's some questions just to tell me if you think it's acidic, basic, or neutral. If the pH is equal to 1.5, the pH is less than 7, so here we have acidic. If the H3O plus is 1 times 10 to the minus 8, that means it's less than 1 times 10 to the minus 7, therefore it's basic. If the pH is 7, it's neutral. And if the OH minus is 3 times 10 to the minus 10 molar, the way I would do this is to figure out the H plus concentration. So I would do 1 times 10 to the minus 14, which is our Kw, divided by 3 times 10 to the minus 10. And this would be our H plus concentration or our H3O plus concentration. Let me figure this out for you at the moment. Let me try. 1 to the exponent 14 negative divided by 3 to the exponent 10 negative. This gave us 3.3 times 10 to the minus 5. 3.33 times 10 to the minus 5 would be our H plus. This is greater than 1 times 10 to the minus 7. Therefore, we have an acidic solution. We also have something you'll be doing in the lab, converting H plus to pH. And this is the formula you use. This is a little bit of an exercise with your calculator because you want to figure out the pH concentration based on the H plus. So in that case, you would take out your calculator. Remember this formula, pH is equal to negative log of H plus. The first thing you should try in your calculator to make sure you're on the same page is the pH will be 7. So if I gave you the concentration of H plus was equal to 1 times 10 to the minus 7, you have to do this on your calculator using the formula pH is equal to negative log H plus. So you have to put this number in here and make sure you get pH is equal to 7. Some calculators you have to punch in the word log first and then 1 times 10 to the minus 7. 1 times 10 to the minus 7 is the same as 0.000001 with 6 zeros. So try this exercise with your calculator. Try this example here. If the H plus is 1 times 10 to the minus 3, you should get a pH of 7. So that's how to convert from H plus to pH. Let's do the reverse. If we were given the pH, how would we convert to its concentration? So this is the same thing as writing antilog, which is a button on your calculator, antilog negative pH, which is the same as equal to H+. So again, an exercise on your calculator you should do before proceeding is write in this, I'll do it in yellow, put in 7 here. So either you type in -7 antilog, or if you have your calculator, you might have to put in the word antilog first, -7. Hopefully you get 1 times 10 to the -7. If you do that, try the example. If the pH is 8.5, what is the H+ concentration? Again, you can either do 10 to the x, which is 10 to the -8.5, which will give you 3 times 10 to the -9 molar. So here are some examples to try on your own. Again, you have to have the calculator you're going to be using on your exam. The equation you'll be using for the first one is pH is equal to negative log of H+. So again, that's the hydronium concentration. And in the second case, the equation you'll use is either antilog or 10 to the minus pH on your calculator, 10 to the minus x will give us our H+ concentration. So try these on your own. Again, I wrote the answers here on the bottom. So let's put the two ideas together where you know how to go from pH to H+. You also know how to use the Kw expression, 1 times 10 to the -14 equals to the H+ plus OH minus. So in this case, the question is, what is the OH minus if the pH is 4.5? So I'll tell you verbally, the first step is to convert the pH to H+, which is the first step we did here. We converted the pH to H+. Once you have the H+, you use the equilibrium constant of water. You know the H+, you know the 1 times 10 to the -14 constant. You can find your OH minus, and I did it here on the right. And we get 3 times 10 to the -10 molar. The next one, you can try on your own, so you can pause the video or give it a try. The question is, what is the pH if the hydroxide concentration is 2.5 times 10 to the -3? So we first convert the hydroxide concentration to H+ using Kw. So Kw equals to, I'll write it out for you, the hydronium concentration, OH minus, is 2.5 times 10 to the -3. And we're trying to find the H+. So in that case, the H+, let me calculate, 1 to the exponent -14 divided by 2.5 to the exponent 3 negative is 4 H+ is equal to 4 times 10 to the -12, and it's molar. And now we're just trying to find the pH. If we know the H+ concentration, we use the equation pH is equal to negative log H+. So use the equation again, pH is equal to negative log H+. So if we plug in this number there, we try log and negative, we get 11.39 or 11.4. Just another short summary. If we notice, we're at pH 7. The concentration of H3O plus is 1 times 10 to the -7. Also, the OH minus is also 1 times 10 to the -7. If we decrease the pH, we have more acid. And as you can see here, there's more acid at pH 3. There's more H3O plus than OH minus. So as you have more H3O plus, it's acidic solution. And likewise, if we're at pH 11, it's a basic solution. You have more OH minus versus less H3O plus. The last topic is buffers. So hopefully you've heard this before. Buffers is the ability to resist changes in pH. So, well, if you did not have a buffer solution, if you added some acid in a solution, let's say of water, the pH will change quite drastically. But if you had a buffer such as H2CO3, that's an example of a buffer, which we'll talk a little bit more detail, the pH will not change too much. So here's a nice picture here. If you have a buffer solution, at pH 7, you add some OH minus, you add some base into the solution, the pH will change very little, 7.1. And if you have, again, that same buffer solution and you added some acid, H3O plus, the pH will not change too much, to be 6.9. So a buffer is made up of a weak acid. We know a weak acid means it is not one of the 7 strong acids. So a buffer solution is made up of a weak acid and its conjugate base. So again, a conjugate base means it differs by 1 hydrogen than its acid. So acetic acid is a buffer because this is a weak acid, and its conjugate base is a difference of 1 hydrogen. Acetic acid is its conjugate base. We can say salt because in terms of charge neutrality, we have this Na, which is Na plus CH3COO minus. We also have here a weak acid. HF is not one of the 7 acids. HF is a weak acid, and its conjugate base is this F minus. So we can also have a buffer solution made up of a weak acid and its conjugate acid. So if NH3 is a weak base, its conjugate acid would be NH4 plus. So 2 cases of if you have a buffer solution, if you have a weak acid and its conjugate base in a solution, or if you have a weak base and its conjugate acid in a solution. Let's see if we have an example here. Which one of the following are buffer solutions? So this HCl and KCl, this is not a buffer solution because HCl is a strong acid, not a weak acid. Remember, it's composed of a weak acid and its conjugate base. For B, H2CO3, this is a weak acid. It's not one of the 7. And here we have its conjugate base, HCO3 minus, with Na plus as its salt. For C, well, these are not conjugate acid bases of each other because remember, conjugate means they differ by 1 hydrogen, okay? And that's not the case here. We have PO4 and Cl. In the last case here, this is another way of writing acetic acid, and it differs by 1 hydrogen. Although you have this K here, but this is just the balancing of the salt, or balancing off because of the charges to make a salt. So how does a buffer work? Well, in this case, we already said that acetic acid is a buffer. This is its conjugate salt, acetate ion, CH3COO minus. So if we had these 2 species sitting in a beaker and we added some acid, we added some H3O plus, it's going to react with the base to give us CH3COOH, this acetic acid. And acetic acid does form, but it won't change the pH too much because this no longer is present very much because it gets eaten up by the C2H3O2 minus to give us this acetic acid. In reverse, if we put some base OH minus into the solution, the acetic acid is going to, you can say, eat it up or react with the OH minus, and you're going to get some acetate ion, which will not change the pH too much. So if we have a buffer solution, again, the same example with acetic acid, you add some, if you look at the left here, you add some acid in there into the solution. Yes, the HC2H3O2 will increase a little bit, but it won't drastically change compared to if we had just H3O plus in there. So it acts as a buffer and the pH will not change too much. And conversely, if we had the same solution, a buffer solution, we added OH, you'll get a slight increase in C2H3O2 minus. Again, will not change the pH too much.